writing my own green screen code. And then on the Macintosh, it turns actually also on the PC, also on the PC, you could basically capture a portion of the image and then replay that in a different part of your screen, right? Um, and then that allows me to use WebEx to project the entire screen that I have in one go. And so, yeah, so hopefully that is it's less of a load on my computer and gives more flexibility on what I can do. Um, because in particular, doing it that way allows us to do the lecture directly on OneNote. Because recently I found out OneNote, um, it's how do I call it? Its updating frequency on OneNote has become so fast compared to in the past. So in principle, what you guys can end up doing is that we can I can just do it directly on OneNote. Yeah. Yeah. Then I don't need QuickTime either. I can shut off QuickTime, and that should be good. Kind of excited. All right. So I'm kind of curious. If you have pretty much done the exam and you're getting the results and plot that I showed you, and it's just you haven't recorded it yet or something like that, please send me like a private message or something so I get a sense of where you guys are, right? Okay, that's good. Um, yeah. When you're doing this thing, of course, you don't want to go off and start recording immediately. What you want to make sure is that you have a code that works, right? You've modified it, you know it works, you have written it out, and then only then record it. So, you do it once correctly, and then you record it and explain yourself, right? So it's a two-step minimum procedure, right? Good morning, GM. Uh, genetically modified. Genetically modified? General Motors? Or did you mean good morning? Or general manager? Oh, there are just like so many abbreviations nowadays. Yeah, oh man, yeah, yeah. So what happens is that at North Carolina State University, there's this professor there. His name is Orlin Velov. He's actually quite a good guy. He's actually really good, Orlin Velov. When I was doing my PhD, he was actually a postdoctoral fellow in the same research group I was in, and his name is Orlin Velov, and we always call him O Man. Yeah, he's quite an incredible guy. Yeah. Let me see. Does anybody have any questions? I can answer. Uh, Rosalie, Matt. Notice you guys have your microphones on, so you guys are ready to talk anytime. So say something. How are you guys doing, Josh? Yeah. No questions? Okay, this is something new. No questions. You guys are kidding me, right? Abdullah, you sure you don't have a question? See, what happens is my experience with exam two is kind of like, do you guys have any questions? Any questions? No questions. I'll tell you guys, I won't be answering questions by email on one-on-one because that's grossly unfair, right? And if I start doing that, then everyone tries to pry as much from me as possible. I'll be replying to emails to no end, right? And so I can't do that. So now I ask in class, do you guys have any questions so I can answer it for the entire class? And no question. Okay, so don't just pile it up all on the last day just before the due date. Okay? I mean, please don't do that. I mean, it's just ridiculous, right? Because you got to get this thing done eventually. There's absolutely zero benefit waiting till the last minute and the panicking, internet goes down, whatever goes down. It's just the wrong way to do things. Uh, any questions? It's 11:44. If you guys have, Abdullah, what's your question? Okay. Will the number of the unknowns t? Yes, exactly. It will be. So what happens is in the past, the number of unknowns was nx minus 2 because you know the temperatures at both ends. This time around, what happens is that you also don't know the temperature at the insulated end. So you have nx minus 1 because you only know the temperatures at one end. The other end, you need to solve for, right? But along with that unknown comes another equation. And that extra equation is the equation that you need for that insulated end. And I think I've pretty much shown you guys how to do it in the last class, right? And so, write that out, explain that out on paper, right? And then implement the code. In principle, if you know what you're doing, this exam is, if you understood what I was telling you, it's a very, very easy exam. It's much, much easier than it looks. Um, uh, yeah, but what happens is, remember, I only wrote down 49 and 50. Especially, I only wrote down 50 just to make it very clear to you what I meant. I mean, absolutely nowhere in your code should you be typing down 50, okay? If you have the two numbers 50 in your code, I can almost guarantee you it's not going to work, okay? So it's when you said figuratively, what I meant to say is when you're writing down or not deriving, it's so trivial. When you're like writing down the Crank-Nicholson equation for the insulated boundary, you access Tj plus 1, that is the same as Tj. And so you just do an algebraic manipulation on both sides of the equation, and that's it. And then you will add that. That's an additional equation that you would have in the Crank-Nicholson equations when you do the Python. Okay. Any other questions? Yeah, something like that. Does anybody have any questions? Because if you don't have any questions, I mean, we can't stare at each other, right? So I keep going. Okay. All right. So let me teach you guys uh, very useful stuff, right? So you got to understand, like, at this point, clearly, because the exam is out, clearly, whatever I teach you now is not going to be on the exam. It's pretty obvious, right? And with the exam there, it's also pretty clear. I can't assign a homework on this either. It's unfair. I mean, and so at this point, you guys are here simply because, you might want to have a guided tour of a book, right? The reality also is you got to understand when you guys graduate, just because you don't have a tour guide like me, it does not mean you cannot just go for a walk in the forest, right? So this textbook, somehow you guys have finagled a copy here and there or purchased one on Amazon or somewhere. Um, it's a book. It's just like a forest. You can go into it for a walk. And there's absolutely no such thing as a useless chapter in this book. This book is packed solid with useful knowledge. And if you're an engineer, every single chapter in this book, in principle, at some point in your career, you'll come across if you actually work as a chemical engineer. Yeah. So let me pass by what I consider one of the most important chapters of this textbook. And it's this section here on heat exchangers, right? And who has heard the word heat exchanger in this class? I mean, of course, everybody has heard of a heat exchanger, right? Who? Let me put it this way. Let me flip the question around. Who has not heard of? Well, actually, you're not going to raise your hand if I ask it that way. So, pretty much everybody has heard of a heat exchanger. Is that right? Is the word heat exchanger kind of rings true? Yeah, Christian? Yeah, heat exchanger? Yeah, of course, because heat exchangers everywhere. So what happens is, let's say if there's any kind of central air conditioning, right? If your parents' home, or actually if the dormitory has even those in-wall air conditioners have a heat exchanger. If you manage to look at the back of a refrigerator, I think nowadays it's at the bottom, so it's very hard to see. There's also heat exchangers, right? So what's a heat exchanger? A heat exchanger is simply you have two fluids and you want to transfer heat to the other. That's it. It's as simple as that, right? And so if you look at this picture here, this is one of the simplest type of a heat exchanger. This one is a concentric tube heat exchanger, and it's parallel flow. Um, I don't think anyone would make a heat exchanger like this. Okay? This is a no-no. Okay? And so what happens here is you have one stream. I think they labeled it as red, which is hot, and it's flowing down. And did you see? And its color becomes more and more faint, which means it's cooling down, right? And what happens is it's a tube inside a tube. On the outside of a tube, right? On the outside of a tube, you have another stream, right? And it's flowing along in the same direction. And the outer tube is presumably cooler, and it's taking away heat from the fluid that's flowing in the center. And that's it. Heat exchanger is a general phrase for chiller or boilers. Yeah, I should call it a general phrase, but it's probably the engineering terminology. Okay. Yeah. So it is part of the equipment. For example, if you have a chiller, just for example, if you have a chiller, right? If you have a chiller, there's many components of a chiller, right? Every chiller, the most expensive part of a chiller is the compressor, right? It's the compressor. There's actually a refrigerant, right, that you compress and expand, right? And when that refrigerant expands, it cools down. Now, when that refrigerant is cold, right, you use that cold refrigerant and pass it through a heat exchanger to take away heat from another stream. So a chiller would have a heat exchanger. A chiller actually would have, it does have at least one heat exchanger and a compressor, right? The reason I hesitated there is because in principle, I should actually say a chiller has a minimum of 2 heat exchange points, but let's not go there, okay? So yeah, this is the simplest, this is a so-called co-current heat exchanger, parallel flow. It's going in the same direction. This other one here is a so-called counter-current flow. And if you're going to have a heat exchanger in which you just have one stream and another stream, and you want the simplest possible design, this is the simplest possible design, right? If you need to, build one, how would you do it? You need to build one is something like this. You go to Home Depot, you basically have your copper tubing, right? And what do? You stick that copper tubing inside another tubing. Of course, this other tubing, most likely you probably want to make it out of plastic because the outside of this tubing, which will be facing the environment, you don't want that to have a high, heat transfer coefficient or high thermal conductivity. And in fact, he'd wrap the outside tubing probably with insulation, right? And then at the ends, you'll cap it out, either cement that or seal the outsides of that, right? So this outer portion, you would seal that, right? And the inner portion goes there. So this could be like a PVC pipe and a copper tubing on the inside, right? And on the PVC pipe at the two ends, you put in two elbows, right? And put that in. So you could easily build one, okay? Now, the important things, one of the important things I'll explain to you is that if you have this kind of a concentric type heat exchanger, in almost no condition should you ever set it up this way, in which your hot water is going, your hot water, let's say if this side is hot water and you're trying to cool that down to cold water, right? And so what happens is on the outside, you have inlet and outlets, right? Under no condition would you go hot water and cold water there too, and then to go it like that, right? Or conversely, under no condition would you have it something like, of course, this is a hot stream and you want to cool it down. So you're gonna put in cold water and out comes hot water, right? Under no conditions would you have it going in the same direction, okay? And I'll explain why mathematically with equations later on. But under no condition do you ever wire a heat exchanger that way, okay? If you route a heat exchanger that way, my gosh, if you work for me, oh, you're first on the fire list at the first opportunity I could, okay? So you never ever do it this way, okay? I'll explain it a bit why, okay? So the way you would do it is you would always do it this way, right? So the way you would do it is, which way would you do it? If you have a hot stream, and you want to cool it down, and you have available to you a cold water source, right? You would, and this stream is flowing in this direction, you would always have your cold water source going in counter current, always, okay? So it's always counter current flow, something to remember. Now let me go a bit more. So what happens is you would also have seen situations like this, right? So the most likely place where, so what happened is you basically have tubes here, let's say the hot liquid, and these things will have fins on them. And the purpose of these fins is to increase the surface area so that you can pass, let's say, another fluid, oftentimes air, across it, right? And have more surface area for heat exchange. So this thing is so-called like a mixed flow or cross flow type heat exchanger. The variety of designs on these are like, just limited by your creativity, right? Yeah, so here are, some more types of heat exchangers, right? Like these so-called very high efficiency heat exchangers, right? Where you have a lot of surface area. Basically, you're trying to get as much surface area between your hot stream and cold stream as possible. And so, these are the variety of, designs that you could imagine, okay? Of course, when you are talking about very high flow rates, right? In like in a big commercial design, where you're making like hundreds of thousands of tons a year, I mean, it's very hard to have equipment like this with very small flow channels for flow if you're trying to flow massive amounts of fluid down, right? So what happens is in most process plants, when they want to increase the surface area for heat exchange, most of the time they have these so-called shell and tube heat exchangers, right? So you probably have heard of these things. They're so-called shell and tube exchangers. And so what happens is you always have two fluids, right, that you want to transfer heat across, right? So you might have a shell side. So you notice there are these baffles here, right? The purpose of these baffles is so that the fluid goes back up and down over. And then you will have a tube side, and you have a tube side that goes like this, right? So when you have these kind of shell and tube heat exchangers, of course, it's no longer as obvious and as clear whether it is counterflow or co-flow, right? Co-current or counter-current flow. Because what happens, notice, is this is going in this direction, then it goes back the other direction. So you might ask, well, in this kind of situation, is it co-current or counter-current flow? You can't tell, right? And so what happens is you might ask then, so which stream do you pass through which one, right? So oftentimes when you're passing in fluids through a heat exchanger, over time the fluid has a tendency, because there's no such thing as a pure fluid, right? Even the engine oil in your car, for example, or even the fuel that you put into your car, right, has a tendency to decompose and leave residues, right? And so what happens is, well, think about it. Which side do you think will be more sensitive to residues? Of course, it will be the tube side, where it's just smaller and harder to potentially clean out, right? And so the decision oftentimes in this situation of which stream to put in which stream is determined by maintenance issues, okay? So there you are. So that's the hand waving stuff, okay? So now there's a portion here, right, that I will go back to later on. I just want to make sure, with the limited amount of time we have left, I want to teach you guys the most important things first in order of importance. And if there's stuff I miss out, then so be it. Nothing I can do, right? And so what happens here in this section here, they talk about something called an overall heat transfer coefficient, right? And so you might recall, right, there are two modes of heat transfer that we have discussed earlier, right? And so in all of these heat exchangers, so let's say if you go to this picture here, right, where you have a counter-current heat exchanger, right? Let's think about this for a moment, okay? So you have a fluid, right? And then here you have this is so let's say you have the two sides, right? So this thing here is the pipe wall. So this might be copper, let's say, right? Or some metal. And then you have another fluid, right? So this is a fluid, and this thing is fluid, right? So you notice what's going on here, right? So inside this fluid here, at this location here, let's say you might have some temperature there, right? And so you might, we might, let's say, call that thing T1, and then we will say label that as T1 infinity. And the reason we label that with this infinity is because basically that is the bulk temperature. So if you were to stick a thermometer in the middle of the stream, sufficiently far from the wall, that's the temperature you would measure. It's the bulk temperature. Now, what happened is that right here, right at that surface of the wall, right, of the copper pipe, there will be also another temperature, right? So maybe you might call that T2, let's say, right? That's going to be at the surface of that copper wall. And then what happens next is that within this copper wall, within that copper wall there, you're going to have what? You're going to have heat transfer by conduction. That thing will be by conduction, right? So you will have, within this copper wall, you will have heat conduction. Okay? And so the heat conduction is characterized by a thermal conductivity of the copper material, right? The heat transfer here in the fluid is governed by a heat transfer coefficient, right? That in this case here will be T1 infinity minus, let's say, T2, right? Within this copper wall there, right, your heat transfer coefficient, right, is going to be minus K and the derivative of the temperature, right? And because this thing is a cylindrical geometry, right, you're going to have a 1 over R derivative of R temperature dr, dr, right? Well, let me not go bother to go to cylindrical geometries, but express that just as some sort of like a thermal gradient in the temperature with respect to a radial position, right? And then on the other side here, you're going to have on this surface there another temperature. This might be, let's say, we call that thing T3, let's say. And then within the fluid here, you might have T4 infinity. That's to designate that now you're talking about this fluid bulk temperature. So you notice here, right, in this kind of, if you want to transfer heat from one fluid across a pipe material, you have some metal, of course, separating the two fluids, followed by another fluid, you have three elements of heat transfer. You have convective heat transfer from fluid to the pipe wall, conduction from the inner pipe wall to the outer pipe wall, so that is conduction, thermal conduction. Then you have another heat transfer coefficient by convection from the outer pipe wall to the outer fluid temperature, right? And so you have to somehow combine together, right? You want to have an expression, right? So that, let's say, if I just know T1 infinity and I know T4 infinity, so I just know those two temperatures, what is the rate of heat transfer that incorporates your knowledge of the heat transfer coefficient on the inside, the heat transfer coefficient on the outside, as well as the thermal conductivity, basically properties of that pipe wall, okay? So we will come back to that after this section on heat exchangers, okay? I just want to make sure I have time to cover heat exchangers. Okay? And so the way that is done, right, is over here, you will see the following, right? So you will see here, there's this UA. Well, what does that UA mean? So this U is referred to as an overall heat transfer coefficient. It's called overall. The reason you call it an overall, right, is because it combines the heat transfer coefficient for the cooling side, maybe the inner wall, the heat transfer coefficient on the hot side, that might be the outer wall, on the outer side, as well as the wall resistance, the resistance of the pipe to conduction, to conductive heat transfer. Okay, and so over here, you will see a few more details here, right? That's associated with the calculation of the so-called overall heat transfer coefficient. That is something we will go back to, right? But at this juncture here, right? So you have some values, right? So over here, right, would be some approximate values that are often seen in actual installations of heat exchangers, right? These values here, let's say, typical values, right? Representative values. So in principle, these values can be calculated for more detailed knowledge of the heat transfer coefficients and properties of the wall material and thickness of the wall material and so forth, right? These can be calculated more exactly. But if you just want to say roughly, what are they like? Well, there you are. So for example, if you're talking about heat exchanger between hot water and cold water, two water streams, that's a typical value, right? This one here is an important one here. This one here, do you see? A steam condenser, right? So you have the water inside the tube and you have steam on the outside, right? Notice this thing can go up to 6,000, right? So remember what I mentioned to you is that if you want to transfer a lot of heat, right, it's always condensation by steam. So you'll notice here a steam condenser. So it's water inside the tube and you're heating that up by condensing steam, which is vapor, on the outside of the tubes, okay? And so that is a steam heat exchanger. And there's more varieties, but these are the two typical values you need to remember. So they're about 1,000 water to water and maybe 3,000 for steam to water, okay? Just rough values. Okay, so how do we proceed with thinking about a heat exchanger? And remember at the start of this class, I made a big deal about making sure if you have the simplest type of heat exchanger, to the maximum extent possible, you want hot water going this way and the cold water going the other direction. You want counter current flow in the vast majority of situations. I think in every situation I can think of, okay? So let's see. How do we go about the mathematical analysis of this, right? I'm not sure it's worth it for me to redraw this at this point. This drawing is way too good, okay? Let's see. Maybe I should zoom into this instead. Let me see. So let's talk a bit about the nomenclature here, right? So the nomenclature. So this textbook here, right? They decided to use the letter I for the enthalpy. So you might recall in our previous textbook, the Universe textbook, we were using H for the enthalpy. And in your mass and energy balances, I'm sure you also use H for the enthalpy. In this textbook here, they're using I for the enthalpy. Does someone care to explain to me why they use the letter I for enthalpy instead of H? It's pretty obvious. Anybody? Why would you use I instead of H for the heat transfer coefficient? Well, I said it. Because H is the heat transfer coefficient. And in a textbook on heat transfer, my God, you'll be using heat transfer coefficient, small h, everywhere. You will be using enthalpy to a lesser degree. And so instead, you rename enthalpy to letter I to minimize confusion. But of course, just remember, I here stands for the enthalpy. And H is for the heat transfer coefficient. And of course, here there's a subscript small h and small c that refers to the hot stream and the cold stream. Okay, so let's see. Let's take a look at this some more. And then you'll see this m dot and m dot h, m dot c. Well, of course, that stands for the mass flow rate, right? So that's the mass flow rate. Okay. So now let's think a bit about this. Okay. Let me see. Can I move it like this? No, it won't let me. I cannot. All right. Okay. So what happens next is that you'll notice there's this letter Q there, right? So what does that Q refer to? So that Q is the amount of heat exchange, right, that occurs. So what are the units of Q, for example? What would be the units of Q? Let's just make sure. So Q, as the way they have written there, is equal to m dot, right? Some m dot, either hot or cold. And then you got the heat capacity per unit mass of the hot or cold stream. So in this case, let's stick with, let's say, the hot stream, right? And then you'll notice there next, you have THI minus THO. That I and the O obviously stands for inlet and outlet, right? So this is, in this case here, you have the inlet and the outlet, right? So you're going to have T of the hot stream at the inlet minus the temperature of the hot stream at the outlet. So the change in temperature of the hot stream multiplied by its heat capacity. So this is units of let's say joules, right, per kilogram Kelvin. And this mass flow rate will have units of kilograms per second, right? So the units of your Q is going to have units of what? It's going to have units of watts, right? It's the amount of thermal power, right, that you could transfer across between the hot stream and the cold stream. Okay? So likewise, you can write down a similar expression for the cold stream, of course. And by energy balance, the amount of heat that was lost by the hot stream has to be equal to the amount of heat, that's power, that's gained by the cold stream, right? You lose it from the hot stream, it goes to the cold stream. Okay? So these two quantities must be equal. Okay. So now the next part of the book, it goes off and says something like this. Delta T, you see the triple sign? That means it's a definition, right? It's a definition. So this delta T, the way they defined it here, is the difference between the hot stream and the cold stream. So if you're reading this book and the moment you see that, the first thing that goes into your head is, of course, you might ask, wait a minute. Up here, there's the inlet and the outlet, inlet and the outlet. Well, down here, there's no inlet and outlets there. So what on earth are they referring to? So what they're referring to is that this delta T, right, is the difference in temperature between the hot stream and cold stream at some specific position along the heat exchanger. So do you expect this difference in temperature to change? Well, why? Of course, because what happens is, well, this is the hot stream, it's coming in. What do you expect its temperature to change as you go down? Its temperature is decreasing. The cold stream is, the temperature is increasing as you go down the heat exchanger. And so this delta T is decreasing. The temperature difference between the hot stream and the cold stream is decreasing as you go down the heat exchanger in the direction of the flow of the two streams. Okay? So let me see. then, so you might be wondering, right, at this point, hey, maybe, right, because what happens is you have expressed, right, you have expressed at this point here, you can calculate, right, the amount of heat that was transferred based on the change in temperature of the hot streams and on the change in the temperatures of the cold streams, right? So you might also be thinking, wait a minute, the reality is that this hot stream across it has some average temperature. And this cold stream across it also has some average temperature, right? And in fact, you can think of this as between these two streams, there is some average temperature difference, right? And you might think that, hey, the bigger the average temperature difference, if you have something that's very hot and something that's very cold, the amount of heat exchange will be much more rapid than if you have two streams that are almost at the same temperature, right? So the difference in temperature, right, at this point, the difference in temperature at this point is what's driving the heat exchange. So if you have, on average, a bigger temperature difference across the heat exchanger, the more heat transfer you would expect, the bigger the value of Q you would expect, right? Well, see, what happens is, the temperature of the, so what happened is the outlet temperature of the cold stream, right, is higher, right, than the inlet temperature of the cold stream. So this is a positive number. That's basically the enthalpy that was gained by the cold stream. As the way it's written here, this is the enthalpy that was lost. The inlet temperature of the hot stream was initially higher and decreases. So this is the heat that's lost by the hot stream. This is the heat that's gained by the cold stream after they both pass through the heat exchanger. So that's the way it makes sense, right? Let's see, next. All right. So let me see. So why does the book oftentimes have cold and hot streams going in the same direction if it's not useful in real life? Because I think at this point here, they really want to emphasize to you not to do this. Okay. So we go off and do our calculations, right? We first do an initial analysis of this thing with the streams going in the same direction, right? Actually, what happens is that the analysis of this problem, the way we're going to go through the equations and analyze the problem, does not depend on which way the streams are flowing. Okay? It actually does not depend. The mathematical analysis, the equations that we would write and the equations that we would solve do not depend on which way the flows are actually going. Except that once you incorporate the directionality of the flows into the equations that we derive, you will clearly see that co-current flow is inferior, significantly inferior to counter current flow. So I think that's, I mean, for me, at this point here, is that if you choose to forget everything I taught you in this class at this point here for heat exchanger, the only thing I really want you to remember is counterflow. Don't ever go co-current, okay? You go co-current, the risk of getting fired is quite high because everyone knows you have no clue what you're doing, okay? So co-current, okay? That's the minimum you need to remember, okay? And at this point, we'll go through more details of how to do the calculation, heat exchanger calculation, okay? So I start with the most important thing you need to remember, okay? Okay. So there's a bunch of, simplifications here. Some of these are to the point of being legalese, more like talking like a lawyer, right? But, so at this point, let's look into this in a bit more detail, this picture here, okay? All right. Okay. So remember what we said, right? That the temperature of the hot stream, this is the inlet, as you go down the heat exchanger, its temperature decreases, right? For the cold stream, there's the inlet temperature and the temperature increases, right? And what happens is that it's the difference between these two temperatures. There's your delta T. And it is this delta T at some particular position there, right? That's going to determine your rate of heat exchange, okay? So This is in terms of the temperature drawn. And over here, there's another schematic, right? So here there's some differential area that's available for heat exchange, right? So of course, as you go down the tube, that area, if it's a concentric heat exchanger, then that's going to probably be the circumference multiplied by some differential length along the pipe, right? So, but it's some differential area that you can calculate. Okay, so let's keep going here. So now this is the part where things gradually become progressively more interesting. Okay. So this expression here is exactly, nothing surprising with that, right? So what does this say? This says is that the small change in the small amount of heat that is being transferred, right? A small amount of heat that was transferred, right, is because the hot stream changed by a small amount in its temperature, right? So notice there's a negative sign there. Why? Because notice in this case here is if the temperature of the hot stream decreases, well, dTH is negative. Negative gives you positive, so that's dQ is positive. There is heat exchange that went from the hot stream to the cold stream. Okay? So now the next part here is that every time you have these kinds of situations that occur, notice it says the only difference between these two is that there's a CH there, right? Okay? So at this point, you look at the text. It says CH and CC. You notice there's CC and there's CH and CC. It's like are the heat capacity rates, right? So you might be wondering, why do you bother to say heat capacity rates? You're probably thinking, I might get that mixed up with CP and CV. Well, don't. So heat capacity rates are simply the heat capacities multiplied by the mass flow rate of the hot stream. The heat capacity per mass for the cold stream multiplied by the mass flow rate of the cold stream. So it's basically heat capacities multiplied by the flow rates. And so you might ask, is it really that important to do that? Not really. Every time you see that, you can just write it that way. But what happens is it's kind of clear at this point. The reason they do this is because we will be using the combination of mass flow rates times heat capacity over and over and over again. So remember this, in every analysis of a heat exchanger, this is the way that they would do it, right? Okay. All right. So now here comes the next part. Do you remember earlier I had mentioned to you this idea of a overall heat transfer coefficient, right? It basically describes that if you have a temperature difference between two streams and there's convection, at the same time there's conduction between the walls, let's say, across the wall of the material, then this U here is basically the proportionality factor that you multiply the temperature difference by and the area to give to you the amount of heat transfer rate that you could achieve over that small amount of area across which a certain delta T is present. So this typical value of U, earlier you saw it for water, it was 800 watts per square meter per Kelvin, right? Right? So you might ask again, Carlos, can you show me again where's delta T, where's dA? Well, it's right here in this picture here. So in this picture here, you'll see where it is, right? So delta T at this particular position in the heat exchanger, there exists a certain amount of area. For this small amount of area, there's so much heat exchange that's going to occur. And this dQ is equal to the temperature difference across that differential area multiplied by your overall heat transfer coefficient, U, which is about 800 watts per meter squared Kelvin for water, and about 3,000 for steam to water. Okay, so everything's clear, calculated, fairly straightforward. Okay, now this is where things gradually get a bit more interesting. Okay, so now you have delta T, right? Remember, what's delta T? Well, delta T is a definition. Delta T is the difference between the hot stream and a cold stream at some location. All right? And so now the next thing you're going to ask is, what does it mean when you have a differential delta T? What on earth does that mean? Because you look at that thing, and first thing what might confuse you is that, wait a minute, we have a delta. Then outside the delta, we have a differential. Remember, the delta, this delta here is saying at some location, right, associated with some differential area, there is the hot temperature and the cold temperature. The difference between that is delta T. Okay. So now you might ask, then what is the differential of the delta T? What does that refer to? Well, let's take a look at this picture here. Okay. So notice, there you are, right? So what happens is that as you go from this area, from this location to this location, and you traverse a certain area available for heat exchange on your heat exchanger, well, what happens is that the temperature of the hot stream changes, the temperature of the cold stream changes. This is your DTH. This is your DTC. So clearly at this point, this is small differential d is corresponding to a differential change because you have proceeded or progressed along the heat exchanger over some differential area. So this differential, this d here, is referring to as you go along and use up, as you go along the area available for heat exchange, right? Okay, so that's the meaning that they're trying to imply there for that small d. Okay. So the next part is the following, right? Okay. So now you say, all right, this is where things, because later on when you see the final result, your response will be like, oh, that's interesting. Wow. How did we do that? Well, usually when you're solving a problem, there's a key junction, which oftentimes is referred to as the crux of the solution. This is the crux of the solution. This is the moment where it requires probably, it's obvious once you see it, but if you never saw this is the part you're going to forget, okay? Notice at this point, it's so obvious, right? If it's shown to you, it's so obvious, right? It goes dq, the amount of heat exchange across that differential area corresponding to this differential change in delta T is this. Look at that. It's dq over ch is dth. And you might ask, why? Well, we just did that. Notice if you go up here, it's right there, right? The amount of heat exchange is equal to the mass flow rate times the heat capacity times the change in the hot temperature. Notice that if you see it here, your response is, yeah, of course. A hot stream change in temperature by a small amount. It has this mass flow rate. It has this heat capacity. So it means that this amount of heat has left the hot stream and gone to the cold stream. So notice when you see it like this, it's so obvious. It's so obvious, right? But notice that if you just scroll down, 2 lines down, and you go here, and you see DTH, how many of you would think and just recall of that equation above? Hey, that's actually dq over ch. It's obvious when it's shown to you, especially when it's right above, right? But for you to think of doing that, I think this is the hardest part of this analysis, actually, which means it's not that hard, okay? So what happens is this part here. So you have the DTC. Well, DTC, what is that again? That's the change in temperature of the cold stream. That arises because you have some heat transfer. The heat transfer divided by its heat capacity rate, that's the amount the temperature has to change by. So that's another way to phrase it, right? There. So now you might ask, well, why on earth would you go about doing it this way? Well, because why? Well, Look at this. Okay? So I might ask, how did you go from this step to this step? What's the deal with that? Actually, you probably be wondering, why on earth did we leave it? Why didn't we just leave it in this way? Why did we bother to introduce dq? Well, see, the reason we have to introduce dq, the differential amount of heat that was transferred over some differential area, if you're solving this problem without looking, what would trigger you to want to do that? Well, the reason you would want to do that is because you know a problem has to depend on your heat transfer coefficient, right? Inevitably, the heat transfer coefficient, the kind of heat exchangers it is, water, 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 steam, the value of U has to come in, right? And how does that come in? Well, you need to have a relationship, right, to the delta T and the dq. And that's how it comes in. The only way you can introduce this physical characteristic of your heat exchanger, this overall heat transfer coefficient, is via dq, right? This is the only expression that has a u in it. So that's why when you're solving this problem, if you never saw the solution, that's what would tickle you to want to do it. I got to get the u in, right? Okay. So now at this juncture, if you think that way, then what is dq? Well, u delta t dA. Well, plug it in. So you plug it into there. Well, there's your u, right? And what do you know? Conveniently, there's your dA too. There's your dA there, right? And then this delta t, well, you're looking at this. Wait a minute. I got a derivative of a delta t. Well, there's a delta t there. So you divide over to the other side. See that? So now I know at this point, when you look at that thing, you're not comfortable seeing that delta t, right? Well, let's look at this side of the equation first. This is the easy side, right? So the dq introduces in there a dA and a u. So there you have a u and a dA, right? Notice that the heat capacity rates are constants. That's the mass flow rate of the hot stream. That's the mass flow rate of the cold stream. These are the heat capacities. So the heat capacity rates, CH and CC, are the operating conditions of your heat exchangers. Those are constant across the heat exchanger. As you go down the area of that heat exchanger, those values are constant. So they go out of the integral. There's a dA in there. Of course, you're going to integrate. And at this point here, you have to make sure if you're going to integrate, you have your limits of integration. That's always where things go bad. Limits of integration. So there's 1 and the 2. So what does 1 and 2 correspond to? Well, clearly they correspond to one end and the other end of the heat exchanger because you're consuming up all the area, right? From one end, and you have differential area, differential area, differential area until you reach the other side, and you basically consumed all of the area available for heat exchange, which is driving the changes in temperature. Okay? So those are your two locations, right? So where would be 1? Well, that's going to be 0. You have not yet used up any area. When you go to the other point, well, that's when you have already used up all the area, right? You see where that thing's going to go. So that's just going to be the total area of the heat exchanger here, okay? Now, it's this side of the expression. The first time you see that, it's not comfortable because you see that delta T. And remember what I told you. This delta T is simply the difference between the hot stream temperature and the cold stream temperature at some position. So don't worry too much about the delta T because what is that? Look at it, right? So that delta T is simply referring to the difference in two variables. It's TH minus TC. So if you're not happy calling that delta T, I don't know, you can call that Z. I guess you might even call that X if you want to. X is equal to TH minus TC. So fine, that's X, right? So X, this difference in temperature, it's delta T. is changing as you go down, right? The heat exchanger. And so that's it. And so as long as you don't get too preoccupied, oh my God, it's a delta T, it's a delta T. How do we take a derivative of a delta T? No, delta T is a single variable. You could call that X, Y, Z, W, whatever you want. Delta T is just the difference in two variables. That's it. And so it's a variable, you can integrate it. So if you have an integration of, let's say, dx over x, what's the integral of that? Well, natural log of x. Then you evaluate that at the two limits of integration. At the two limits of integration. So now you notice this is where it gets interesting. Now, what happens here? Notice we write down. This is the delta t at one side, or you say we have not consumed any area yet. And then this is the delta t on the other side of the heat exchanger, which means we have gone through the entire heat exchanger. There you are. Now, you notice at this point here, if you look at this equation there, right? See, Jared, right? See, that's the interesting thing, right? See, what happens is, you notice, right? You notice that 1 and 2 are defined simply in terms of two locations on the heat exchanger, right? Position 1 is where we're integrating over the area, right? So you would choose one end of the heat exchanger and integrate across the heat exchanger until you reach the other side. So now notice your natural tendency when you're looking at this problem is you keep focusing on inlet, outlet, inlet, outlet, inlet, outlet, right? That's your natural tendency. Don't do that. Because what happens is that if you say inlet, outlet, which one are you referring to? Inlet of the hot stream or inlet of the cold stream, right? So let's not do that. Let us just simply analyze this in terms of the amount of heat exchange, right, that occurs as we go from one end to the other end of the heat exchanger. Okay, that's it. So now, if you think of it that way, right, look at, let me not jump the gun here. At this point here, right, there's this set of, there's this, how do I describe this? This thing's almost by tradition, right? And so let me not dwell too much on this. I'm going to skip this section there, and I'll come back to it in a moment, okay? I'll come back to that in a moment, okay? But what happens is, look at it this way, right? So it goes something like, they call it a parallel flow. That's basically co-current. It's co-current. They're going in the same direction, okay? Okay, look at it this way. So when we say the delta T, the difference in temperatures at one end, at position 1, well, what is that? It's the temperature of the hot stream at position 1, the temperature of the cold stream at position 1. Now you notice, this is where it gets interesting. If you have a co-current, meaning you say it's going in the same direction, well, guess what? At position 1, that's the inlet of both streams. You might ask, can I do it on the outlet? It's the same answer. You'll get the same answer. It doesn't matter whether you say position 1 is the inlet of both streams or the outlet of both streams. You get the same answer. It will work out. Okay? What happens is, notice that now at position 1, if it's a parallel flow, at position 1, it's the inlet and inlet of both the hot streams and the cold streams. At position 2, when you're calculating that delta T, it is the outlet and outlet. Now, of course, you want to venture a guess. So if you have a counterflow heat exchanger, what happens? Well, you notice that our mathematical analysis is still all the same. Everything is the same. The only difference is that now, hey, if it's counterflow at position 1, if we say that this is the inlet of the hot stream, well, this one here is going to be the outlet of the cold stream. And if this is the outlet of the hot stream, if it's countercurrent, then this one should be the inlet of the cold stream. Did you see? Isn't that beautiful, right? And so what happens is that our analysis here, well, not our analysis, this is what every engineer has done, right? Whenever they talk about heat exchanger, that's what they're doing. So the analysis that was done here, right? You do not start talking about inlet and outlets. You simply say at two positions, we're going to integrate across the amount of heat exchange as the temperature difference changes along the heat exchanger. When we do the integration, eventually we will need to integrate. We need to have limits of integration, right, on the temperature difference. Well, it's only at that point that you say, what's the temperature difference at this side? What's the temperature difference on the other side? And those temperature difference at the two ends are set by whether you have counter current or co-current flow. Okay? So now let's talk a little bit here. Okay? And so this part, right, you'll notice that at this juncture here, they did some sort of, maneuvers, right? And it's no big deal. So at this point here, they started going the other way around, right? So notice, what is this equation? Do you see? 1 over CH is this. What is that? Well, that's exactly what I just showed you at the very start. It's very easy to forget these things if you look at them differently. So notice at the very start here, what do we have? We have up here, we say this guy here. Yeah, did you see this expression here? The heat flow rate Q is equal to the C, right? The heat capacity rates multiplied by the temperature change in the hot stream. The same heat is the heat capacity rates of the cold stream times the temperature difference of the cold stream. Did you see? And so we're just applying that. We are just applying that and substituting that into here. Okay? So did you see? So the heat flow rate Q, right? The heat flow rate Q is equal to what? It's equal to the CH, mass flow rate times heat capacity, multiplied by the temperature change in the hot stream as it goes from the inlet to its outlet. That's it, right? And so what's the next step here? So the next step here is just a little bit of algebra. Well, its common denominator is Q. So the Q goes out. Did you see the Q goes out? And you have the hot stream, right? You have cold stream, cold stream. Now notice what they did here. What they did here is that they highlighted this is inlet, that is inlet, that is outlet, that is outlet. Why did they do that? Well, in this situation there, you do that because in this case, we have a co-current heat exchanger, and you want to focus on, right? Remember, on this side of the equation, you have delta T, differences in temperature at some location. On this side here, you have differences in temperature. Well, if you want to rearrange that, it behooves you to rearrange that so that you're also expressing temperature differences at some location associated with 1 and 2. So you do this algebraic, very minor algebraic maneuver to focus attention, right, that you have a delta T. This one is the delta T at position 2. This is the delta T at position 1, the temperature difference. Now, of course, if you have a counter current, then what would happen? Well, then this at the inlet, this would be the outlet. At the outlet, this would be the inlet, right? And that would also correspond to the proper delta T's. And so now at this point, you notice there's this natural log thing here. Well, you divide that across and you move Q to the other side, okay? So now at this point here, Q is what you really are after. Q is, that's the amount of heat energy that can be, that's a heat transfer rate. That's the power, that's a heating power that you can transfer between the hot stream and the cold stream. And how is that decided? You have this value, U. Water, that's about 800, right? Watts per meter squared, Kelvin. Area, that's the size of your heat exchanger. And then on this side here, you have your delta T2, delta T1. Those are the temperature differences at the two sides of your heat exchanger, divided by the natural log of the ratio of those temperature differences. Now, this expression here, difference in the differences in the temperatures divided by the natural log of the ratio of the differences of the temperature has an extremely, extremely widely used term. This guy here, LMTD, log mean temperature difference. Okay, if you ask me, why is this thing so important? Well, if you ever get into an interview for a co-op job or something, and I said, oh, I took transport one. What did you learn? Oh, we learned about this, that. Oh, I also learned about, did you learn anything about heat exchangers? Yeah, because heat exchangers are everywhere. The chances your boss wants to make sure you know something about heat exchanger, pretty darn high. First thing they'll ask you, what do you know about heat exchangers? You say, oh, I learned about the log mean temperature difference, LMTD. Okay. If you say something like LMTD, right? LMTD. What did you learn about heat exchangers? LMTD, log mean temperature difference. At that moment there, if you say that, chances are you're probably off the hook already. At that point, if you say, I learned about LMTD, log mean temperature difference, at that point, the person interviewing you is going to switch gears. It's his turn to show off how much he knows about heat exchangers. Then he's going to start talking. Just nod your head. Yeah, you're right, and you're done. You're off the hook. Okay? That's the joke of an interview, right? Is every interviewer wants to show off how good they are. Give them the chance. So LMTD, don't ever forget this word, okay? LMTD, log mean temperature difference. Where does it come from? They won't go there. It's only if you have an exam with me, I'll hit you with that. On a real job, they won't ask you that, okay? But that's where it comes from, log mean temperature difference. Okay. 1 minute left. I have some more, good, get ready for an interview type of heat exchanger, kind of like cheat sheets here. We'll talk about this in the next class somewhere tomorrow, right? And the next two things that are very close are like NTU and epsilon, your so-called effectiveness, right? Can't type effectiveness. But really, if you're at an interview, heat exchangers, the moment you spit out LMTD and you spit out NTU, net transfer units, you're done. You're off the hook, I think. Okay? So we'll talk about those so you actually know something about them in the next class, and we'll actually do some calculations. But that's for interview purposes. That's what you need to know. Okay? All right, so it's 12:45, so I have to end in that way. Sorry. Okay. So I'll hang around if you guys have any questions. I don't have a class after it, so I can hang around for as long as you guys want. Log mean temperature difference. Yeah, so let me show you. So log mean temperature difference, right there. That's a log mean temperature difference. Okay. So it's just like, what the heck is log mean? Well, the first thing to remember, right? There's something called a log mean. Okay. So I know you've heard of a mean, you've heard of a mode, you've heard of a median. Some of you might have even heard of a geometric mean, right? Of two numbers, a geometric mean. So of course, the average, if you have two numbers, is A plus B over 2. That's your usual average, right? And then the mode and the mean requires more numbers. Then the other one, this is your regular average, right? That's your mean. And then there's the other one, which is called a geometric mean, right? I don't know if you guys seen this in high school. So it's the square root of A times B. That's a geometric mean. And then there's another one that's used in statistics and mathematics, which is called a log mean, right? A log mean is going to be A minus B divided by the logarithm of A over B. This is a log mean. So this expression here of a log mean is used not just here. So for example, this log mean, you will see this again in transport 2, in mass transfer. You will see log mean in other disciplines too. So it's an average. Believe it or not, that log mean actually ends up lying somewhere between A and B. Okay? If you actually put in two numbers, you'll find that it actually lies somewhere in between A and B. Okay? There's some sort of an average. So what happens is that log mean temperature difference. Why temperature difference? Because notice it's the temperature differences at positions 2 and at positions 1. It is the temperature difference at the two ends whose logarithmic mean you're getting, right? So log mean has its own mathematical definition. This is the mathematical definition of a log mean that's used in many fields, many areas of math and science. We're taking the log mean of the temperature difference of the delta T at the two ends. So that's why it's called LMTD, log mean temperature difference at each ends. Sorry, too late, Abdullah. Okay, next question. I can't do that anymore. There's only like 18 students left. You want to ask you an exam question when there's 18 students left. I can't do that, right? Well, come on, we are a job placement agency, right? At this point, here, we're just a job placement agency. Yeah, ask me on Friday, right? It's fair, right? Hello. More questions?
Carlos.
Hi.
I also had a question because I was trying to do part 1 of the exam last night, but do you want me to ask it on Friday?
Yeah, ask me on Friday,
Okay.
right? Because it's so unfair, right? There's only like 18 students left, right? So,
Yeah.
you know, I can't do that, right?
Okay.
You get ready with the questions, okay? Please,
Yeah.
you know, work through as much as you can.
Yeah.
Get as much of it done as you can. If you get stuck somewhere, keep going. Even if you get stuck somewhere, keep going, right? That
Okay.
way you have a accumulation of all of your questions. Because as long as it's in front of everybody, as long as it's in front of everybody, I'm willing to answer anything, almost, right? Because it's fair, right? Okay. So
no, that makes a lot of sense. I meant to get on before, but I couldn't. So, but I'll ask it on Friday.
Yeah, Friday. Okay, Friday. So everyone's around, so it's fair. Okay.
Okay.
Otherwise, I'll get complaints up the wazoo on this. Okay.
All good.
Yeah. You take care. All right. Okay. More questions? Anybody? It can't be exam related because it's unfair. I mean, there's only 17 people left, right? Okay. Yeah. Have a great day too, Rosalie. Can we ask questions? Part discussions. Um. Yeah.